All right, it is now 11 o'clock here in Central Time at the Sencore headquarters here in Sioux Falls, South Dakota. So we are perfectly on time to get this show on the road. So thank you all for joining us for the virtual NAB with Sencore. This is first a series of webinars that we'll be doing over the course of the next month or so, in addition to some product presentations and things like that. But the first one will kick off with a SMPTE ST2110 technology discussion and kind of dive into some Sencore products and things like that at the end. So I hope you all come in looking to learn, looking to figure out how to get solutions for 2110. Whether it's products or systems or analyzers or something like that. I think we'll be able to learn together today. Just to talk a little bit about the virtual NAB webinars that we'll be hosting in the coming months. Obviously, there's the 2110 one today, but there's also one on May 7th. That'll be talking about ATSC 3.0. May 14th, talking about a new product launch actually from Sencore, the signal collection platform. And then May 21st, talking about some of our new product lines for the commercial AV market as well. So be on the lookout for those registrations. We'll be posting those up obviously on social media and doing kind of like email announcements and things like that. So, but all the webinars will begin at 11 a.m. Central Time, just like this one. So be on the lookout for that. And yeah. So just kind of doing a little bit of an introduction here for the speakers and panelists today. So my name is Aaron Doughten. I will be the main presenter here. I'm a product manager here at Sencore. Then I also have with me Seth Vermalm, one of the panelists. He is a senior product manager here at Sencore, in addition to Jason Dabbert, another panelist who is account representative with us. Contact information, or at least email address, is there. So, if you want to take any discussions offline or have additional questions, want to do a deeper dive into, product demonstrations or just have a little Q&A or something like that, feel free to reach out to us. We aren't shy and are used to answering questions and things like that. So on the topic of asking questions, we do have a Q&A function actually with this Zoom presentation. So feel free to ask questions, and then as we go, we will try to answer as many questions as we can during the section breaks, and then we'll also have a final Q&A at the very end of the presentation as well, to try to kind of have a little back and forth with the audience and see what we can learn from each other. So I would like to kick it off a little bit with a fairy tale, if you will. Way back when, there was a bunch of people from the Video Services Forum sitting around a bunch of 100 gig switches and wondering to themselves, how can we use up all of this bandwidth really, really quickly? Some of them said, maybe we can do some file transfers, maybe we can do some web hosting, maybe we can do any number of things with data. And then some guy with an evil smirk said, let's do live uncompressed video and audio over IP with all this bandwidth that we have. And so yada, 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 we now have SMPTE ST2110. But joking aside, this is a technology that I think is a very logical step when we think about all of the available hardware, all available bandwidth, just processing power and things like that. And with modern technology, I think this is a very logical step for the professional media environment. So what we'll be doing is talking about this technology, actually the system of technologies that make up the SMPTE ST2110 family, talking about things like PTP and traffic shaping and control. So how do those IP packets and how do these technologies flow through an actual IP network? We'll also talk about some advantages and challenges of using 2110, deploying 2110, things like that. Sencore has learned, Sencore has heard from our customers and vendors out there, and just kind of our exposure to the market and kind of what to look out for. And then look at some of the technologies that are up and coming with 2110. There are some very interesting things coming on down the pipe that I think will kind of mix things up a little bit, and definitely put some places in the market where products will have to react to, which obviously Sencore is keeping an eye on. Then we'll finish up with ST2110 and Sencore. So what products does Sencore have that can help you guys achieve your goal of deploying ST2110 technologies and systems and things like that? So we'll highlight those. And like I said, we'll be having some pauses during the entire presentation for some Q&A and things like that. So Jason and Seth will be helping me kind of answer those questions and have more of a conversation with you guys. So let's start it off with talking about the system of technologies that make up the SMPTE ST2110 family. So it is truly a system of technologies that I think people maybe with not a very in-depth understanding, maybe just look at SMPTE 2110 as kind of an all-encompassing technology, which it's actually not true. We actually have a family of technologies. You know, we've got ST2110-20, which is specifically geared towards uncompressed active video over high bitrate IP networks. Then we also have -22, which is a new thing. I'll hint at this a little bit better or a little bit more in the up and coming section, but this is actually CBR compressed video over these high bitrate networks. And so don't get that confused with HEVC or H.264 type compression. We're talking about light compression, very low latency, lightweight stuff to try to drive down some of the you know, really high bitrate video like 4K or 1080p 60 to fit into a little bit smaller pipes. But like I said, I'll talk about that a little bit more detail in a following section. Then we also have our audio standards, -30 and -31 for moving PCM digital audio, and also AES3, which is compressed audio essentially. And then metadata, and then the timing and synchronization standards as well. And then there's an additional piece about this that I will talk about, which is the control and monitoring piece. So this is AMWA NMOS control API. Is actually a combination of a lot of different groups within the industry that have come together to try to define a control API in order to not only orchestrate the pieces of equipment that are used to generate 2110 or receive 2110, but also help control the actual environments themselves, like the actual, you know, your IP networks, your tally, your scheduling, your, you know, anything that you can think about in a, you know, normal or a traditional broadcast network. Being able to do these things with a, I don't want to say a generic API, but at least an API that everybody can follow and design products and functions against in order to orchestrate 2110 systems. And I do want to point out that, you know, these are all brand new standards technically, but a lot of them actually leverage very old standards from, I say very old, from like the 80s and 90s even. So like RFC and SD, like SMPTE standards, IEEE standards in order to, you know, reference those old technologies, proven technologies, but just deploy them or make a standard in them for them with regards to, you know, moving really high bitrate streams over IP networks. So it's just a contextual change essentially that allows us to create these SMPTE 2110 standards. But for instance, SMPTE 2110-20 is based on RFC 4175. PCM digital audio is based on AES 67. The ANC data standard, SMPTE 2110-40 is ST291. And even like PTP is based on IEEE 1888. And then there are some specific SMPTE standards based around that standard in order to give it context just specifically for video. So a lot of these things have been around for a long time, but like I said, they kind of adapted those things to kind of build this system, a system of technologies. So another thing I really wanted to point out, and I wanted to make a comparison, I guess, to maybe SDI and then talk about SMPTE 2022-6 a little bit. But then also talk about the encapsulation technique that really gives SMPTE 2110 its unique ability and its huge advantages, and especially in production workflows. And one of those is the independent essence packaging. And what I mean by that is taking your video, audio, and ANC streams and making them completely separate packet flows. So in other words, the video rides in its actual own group of IP packets, so does audio, so does bank. They aren't combined into a single IP stream that needs to be received and parsed and all of that kind of business. This is all completely separate, which is very different from, say, SDI, or even SMPTE 2022-6. So an SDI, obviously, it's a it's an electrical signal over a BNC cable. It goes through some switches and relays and things like that. And I think we all have a very good understanding of getting from point A to point B on an actual physical cable. That holds the video, that has your audio, that has your ANC data, and your active video region, your vertical blanking interval, your horizontal blanking interval, and then all of your ANC data rides along inside those horizontal and vertical blanking intervals. SMPTE 2022-6, which came before SMPTE 2110, was essentially taking that SDI signal and chunking it up and actually shoving it directly into IP packets. So in other words, your video, audio, and ANC data essentially was in a single flow, which is easy to manage, fairly easy to synchronize and things like that, but it wasn't really getting us the advantages that we wanted out of, using IP technologies and getting some flexibility out of the system, where this encapsulation technique very specifically helps 2110 stand out from what I guess would be a traditional broadcast workflow. And we'll talk a little bit more about the advantages and what these individual flows get us in those environments a little bit later in the presentation. So diving in a little bit deeper into SMPTE 2110-20, how do we put those, that video stream into IP packets? So really what we're doing is, taking those, the samples, or we're sampling pixels, and we call them pixel groups or P groups, is do a chroma subsampling in order to get integer number of bytes. So in other words, what we're doing is subdividing all of that video into groups of pixels, or P groups, that allow us to fit them into IP packets very evenly in an organized way. And what happens is when we start to subdivide or divide up those pixel groups, what we do is we then assign them a particular timestamp, and that timestamp is referenced for an entire video frame. So if you even capture some 2110-20 traffic with Wireshark, for instance, you can actually look at the RTP timestamps, and you'll notice that many IP packets have the exact same RTP timestamp. Well, that's on purpose, because that RTP timestamp is actually just one video packet. And then we can actually look at the header here, the RTP packet header. You see a little M bit there? So the M bit is either a 0 or a 1. And if it's a 0, that means you're on the same video frame. And once that is marked at 1, that means that's the end of the video frame, and your next packet will be a new video frame. So that's kind of how this is all organized and packaged and kind of shoved into IP packets in a little bit more organized way compared to SMPTE 2022-6. Now, audio, on the other hand, it's much more simple, I guess we'll say. That I'm not sure if simple is maybe the right way to say it, but especially for linear PCM audio, really what we're doing is taking those audio packets and really placing them directly into an IP packet, which is much simpler than video. There's no payload header. The audio packets are sampled at a rate divided by 8, just to make them divisible and be able to be packaged into IP packets in at least an organized way. And -31 is a very similar way, just with compressed audio, which preserves AES3 bits of audio samples. And here we have some just a discussion about the different receiver classifications with audio. So it is recommended in the SMPTE standards that at least 8 audio channels be carried in a single IP flow. And the reason for that is because if we were just doing 1 or 2 channels, it would not be an efficient use of IP packets at all. In fact, there would be quite a bit of null packets per IP packet, which it's pretty obvious that that's not very efficient. So what we're doing is trying to shove, I guess, as many audio channels into a particular IP packet as we can to be more efficient. But what we have to be very, very careful about is the sampling rate, and then also the packet times, or the inner arrival times of those specific packets. So here we actually have these classifications, A, AX, B, BX, C, and CX, and just depending on what the sampling rate is and how many channels are actually being carried in that particular audio flow, we can have a 1 millisecond timing, which is 1 millisecond between IP packets or audio packets, or we have to tighten it up depending on if we have a great number of audio streams, so up to 64 for 48 kilohertz, or up to 32 with 96 kilohertz audio. We actually have to tighten up those the IP inner arrival time so that we don't, you know, I guess, outrun the video or outrun the processing needed to be able to parse out the audio and do what you need to do in terms of, you know, if it's audio mixing or whatever the process is that needs to receive these types of streams. We just make sure we are paying attention to packet pacing and the number of audio channels. So moving on to metadata, you know, even a smaller number of bits and stuff like that compared to audio. This is actually based on, you know, the ANC standard, you know, SMPTE 291, but we're just taking the ANC data, and it even includes the, you know, the line, the horizontal position, the DID, the SDID, and, you know, making individual packets that have all of our ANC data. And this can be anything from VPIDs to closed captions to teletext, you name it, anything that we're really used to in a traditional broadcast SDI signal can be put into the SMPTE 2110-40 packets quite easily and still use the DID and SDID and all the things that we're used to in terms of a data structure. So it translates quite nicely. And keep in mind, this only carries active lines only, so it's not a copy paste of your ANC and, or I guess your VANC and HANC. It only carries what is actually active data or what you've selected to pass into the -40 IP packet. So again, a little bit more efficient. Obviously, it's not huge gains here with the metadata stuff, just because of the bit rates are quite a bit lower than video and audio. But it is just a more efficient way of carrying that data. All right, so that kind of concludes the first section talking about the, you know, transport technologies a little bit. So I kind of wanted to reach out to the panelists and maybe look at some questions or something like that that have been asked.
Sure, we've got two questions here.
Okay.
I'll do the first one here, Jason. Can compressed audio like Dolby Digital and ATMOS be packetized in SMPTE 2110? Oh,
yeah, absolutely. So that one would actually be a part of probably SMPTE 2110-31 specifically. So that would be the AES3 transparent transport. So that would probably be assumed to either be already pre-mixed or something like that, and kind of encoded as Dolby Digital plus Atmos, and so that would ride along in -31. Now, I'm not entirely privy into the standards and how that would actually translate into being implemented from an engineering perspective, but that's definitely the technology I think would be utilized in order to carry those things. So yes, absolutely.
All right, Aaron, then the other question we have is, do you support ST336 protocol for metadata transmission?
Yeah, so that would also probably be a part of the metadata transmission from ANC and VANC, is like, at least I think that's what that's referring to. I don't know specifically what ST336 is necessarily, but being metadata that would most likely be carried in ANC or VANC, I don't see how that would be a problem to be carried in -40. Let me go to the slide there. I think as long as it's, you know, put together in terms of regular ANC or VANC packets, then you would be good to go to carry it in -40 as well. All right.
That's good. Yeah.
Good to go. All right. I think I will continue on with the talking about PTP, which is the synchronization mechanism of a SMPTE 2110 network, but then also talk about traffic shaping and control. So traffic shaping is going to be your, oh, let's see, how do I want to say it without being too complicated? It's essentially your receive buffer models and the rules and regulations for which a transmitter of 2110 has to adhere to in order to be, let's say, 2110 legal, I guess. Anyway, we'll get into more details about that and put some graphics towards the conversation. And then the control mechanism will be talking about NMOS and kind of what our exposure to NMOS has been here at Sencore and things like that. All right, so talking about ST2110-10, this is the system timing and definition standard. So I hate to make this parallel, but I think it's the easiest way for people to grasp this technology, and it really is essentially it's the gen lock and time code of a 2110 system. So back in SDI, we had gen lock to get into a frequency alignment, and then also time code to get into a phase alignment. And what I mean by that is we want every single video frame to happen at the exact amount of time, so that way when we're switching between different monitors or different camera feeds or something like that, you're not cutting in like halfway through a video frame and you get this weird kind of wiping action on the screen, and it just doesn't look very nice. So what we do is we frequency lock everything to a particular video frame start and end point. Time code allows us then to synchronize on an exact video frame or a moment in time, if you will. So let's pretend you've got like, I don't know, 30 camera feeds coming from a contribution sporting event. And all of those cameras are kind of, they're pointed at a particular, a point in the field. Maybe there's, a play going on. And they all need to be synchronized and switching between different camera feeds in that kind of exact moment of time to get the different angles and stuff like that of the players. Well, we want to make sure that we're all synchronized on that exact moment in time, or else you're like skipping like either forward or into the past, and then you got to like fast forward, and it's a little awkward and doesn't look very good to the audience. So what we want to do is do that phase and frequency lock of video, audio, and metadata packets in a 2110 network in order to mimic what we had with GenLock and timecode. So this is actually, like I said before, based on IEEE 1588, which is, again, a pretty old standard. I think it's actually back in the 80s, maybe. And then ST 2059-2, it's actually -1 and -2, kind of take that standard, that IEEE 1588 standard, and kind of translate it into what has context to a SMPTE 2110 system. And it's really kind of all about utilizing timestamps based off an epoch time in order to synchronize, your video frames, your audio packets, your metadata packets, so that everything arrives in this kind of synchronized way, just like GenLock and timecode allowed us to do. And looking to the graphic there that I shamelessly stole out of a SMPTE document, I did give them a little bit of a call out there at the bottom, but kind of shows you how a PTP network is set up, or at least the PTP signal in an IP network is set up. This is actually quite generic, just to try to help everyone understand the general concept. But what you essentially need to do is have a PTP signal that is sent through an entire IP network, and then every single device and function has to synchronize to that PTP signal. And PTP signals, by the way, are created by PTP clock generators that are then hooked to usually a GPS signal that allows them to, kind of globally sync to the exact same time. So not only are all the pieces of equipment synced, but also the routers and switches are synced. Pretty much everything is trying to speak the same language or be timed in a very even method. This can get a little messy when you have like geodiverse locations, like say I have a network here in Sioux Falls, South Dakota, and maybe there's another network in, I don't know, New York or something like that. And what we're trying to do is share content between the two. Well, if they hit both of those networks need to have PTP clock, that you can't necessarily use the PTP clock from Sioux Falls, South Dakota in New York because of IP jitter and just the latency of getting from here to there. That would actually be enough to cause some issues with synchronization. So what you would need to do then is have a grandmaster PTP clock in Sioux Falls and also in New York, and then they would both be synchronizing to hopefully the exact same reference time in order to kind of localize that time frame. So hopefully that didn't completely confuse everybody, but that's the general idea of PTP and how grandmaster clock works across a 2110 network. All right. So how does PTP exactly communicate with devices and things like that to get them to frequency and phase lock? So what the PTP Grandmaster clock does, it actually sends out these what are called sync messages, which they're just a multicast sync message that's broadcasted to every what is called a slave device. And the slave device can be a router, a switch, a receiver decoder, a multiplexer, I don't know, an audio mixer, anything really that's handling any of these 2110 streams. So you get this sync message, and then you reply with a delay request, which that allows you to actually calculate your phase offset with the network delay and the time difference between the synchronization and the delay request. That gets you your phase alignment. But then we also do calculate our frequency offset as well. And the frequency offset allows us to dial in our actual clocking mechanisms, you know, for packet pacing and RTP timestamps and all kinds of things. So your video and audio and metadata clocks are all synchronized to this PTP Grandmaster clock. So everybody's, you know, doing everything essentially at the exact same time and trying to send out packets in a relatively organized manner, and all the PTP timestamps line up with anything that's happening in a particular moment in time. So I gotta give a shout out to Amir and at Fox. I saw this on his LinkedIn profile. I'm pretty sure he made it. Anyway, I thought it was a beautiful graphic that actually did a very good job of showing what it looks like when everything in a PTP network is actually synchronized versus when it's not synchronized. And again, the gen lock and time code thing, there's definitely some parallels here, but obviously the technologies are quite a bit different. But here you can see on the very left-hand side, we're gonna just, you know, arbitrarily start at 0 and actually go into what would be 1 second passing in time. So this is actually 720p 5994 video being transmitted and synchronized in a PTP network. So here you can see the Grandmaster clock has kind of marked this as your start position. This is what we're frequency locking to that particular frequency, and we are now phase aligned with the PTP clock. We're now going to deliver this video frame over the course of 2,160 packets up until this then synchronization. You can see the little M bit's been flagged. So my frame is done. Frame 1 has been broadcasted. Then we keep continuing on with frame 2. Again, the M bit's been flagged, new frame, and we're all synchronized on this actual RTP timestamp Grandmaster clock signaling. Now here you can see on the bottom, this guy is not paying attention to PTP. He is not synchronized to PTP. So you can see as frames are coming in, we haven't even fully received this particular video frame, and it just gets worse and worse and worse as we go on and on. So in this case, in the description that I was talking about, or at least in maybe the application I was talking about, when you're switching between camera feeds, and you're switching between camera feeds for this top video. So say you have maybe 4 or 5 videos that are all synchronized and they look fantastic, and you're switching on these particular boundaries that the PTP clock has given us, you're gonna have that very nice clean switch between all of the video feeds. Now, if you try to switch to this guy on the bottom, yeah, you're gonna like interrupt like halfway or partly between an actual a video frame. It'll just be an ugly cut, or you might have to buffer it or even offset it something. And say if it's like a video editor or maybe an audio mixer or something like that, you're having to like weirdly compensate for this timing mishap. You know, just like you would with genlock or timecode, you're almost making up for the mistakes inside the actual network. So anyway, great graphic. Thanks, Amir, for making it. Sorry I had to shamelessly steal it from you, but I did give you some credit. But yeah, I thought it was a very good representation of what that looks like in the network. All right, so moving on to SMPTE 2110-21. So let's pretend for a second everybody is PTP synced. We are phase locked, we are frequency locked, everybody's happy. Well, that's great and everything, except now we have to worry about buffers. And we're talking about, well, see in the graphic there, I have like megabits per second. That's sort of a lie. But we're talking about gigabits per second worth of data that we're dealing with, especially in terms of like HD, 3G, you know, 4K video over a 2110 network, you know, gigabits and gigabits per second we're talking about here. And so there's been a couple leaky buffer or leaky bucket models defined in dash 2110 in order to kind of dictate what the sender's packet pacing looks like. We have 3 different kinds of packet pacing profiles, if you will, that senders can fit into. The first one is the wide for bursty senders. So this would be a bursty sender might have a buffer of about 720 packets for, I guess, from a receiver standpoint, in order to receive a wide sender signal. We would need to consider about a 720 packet buffer in order to be able to receive something like this. Now, this is really for more software-based video sources, maybe like a video editor, you know, for software-based for making graphics and things like that, or even cloud implementation. So we would expect anything fitting into a wide buffer model to be quite bursty, which makes sense from a software-based video source. You're going to have that kind of burstiness from software or something running on COTS hardware or something like that. Then we have the next 2. You have narrow linear, and then you also have narrow. So narrow linear is interesting because it's very tight timing, very, very tight timing. And then narrow is really for hardware-based implementations, where it actually has no packets during VBI and VANC. So it's kind of, it's almost timed and delivered exactly like SDI. So this would be really close, or I guess be beneficial for like live events and things like that. But what's interesting is your narrow linear and your narrow can't receive things from a type W sender. They just don't have the buffers in order to handle the burstiness of a wide sender. And to kind of paint that picture for you, a type N receiver might have a buffer of about 9 packets, or a type W receiver, like I said, would have about 720 packets. So that's quite a bit of burstiness when we're talking about like gigabits per second of information. So, you know, you kind of have to be careful about when you look at how you're defining your network and what pieces of equipment you have in your network, what are they adhering to from you know, a sender burstiness model, just so that everybody plays nice inside a network. All right, so talked about the system timing and the traffic shaping. Now I wanted to dive into the AMWA NMOS control API. So this is the API that's being defined right now, actually, as we speak. A lot of pieces of it are done, had a lot of kind of dirty interops to make sure that everything was working between all the different pieces of equipment, things like that. But I wanted to highlight certain sections of it and what they're trying to accomplish with the API. And first off is ISO4, or the NMOS discovery and registration. And so what this part does, it essentially, you know, what it registers. So every transmitter, every receiver, anything that needs to, you know, send or receive a 2110 stream registers with the network. So what devices are on my network? Then also, when you start sending a 2110 stream or a bunch of streams, whether they're video or audio or metadata or something like that, we also describe those streams. So what kind of video is being sent in this particular IP stream? Is it 1080p 60? Is it 422 10-bit? Is it HDR? What kind of frame rate is it? Like all of that kind of information is then registered with the network. So that way, when any transmitter wants to receive it, it kind of gets a table of contents, if you will, of what that IP stream looks like. So it's not caught off guard or accidentally, you know, asked to receive some 4K stream, and maybe it only has like a gigabit interface or maybe a 10 gig interface, and then all of a sudden it just, you know, the equipment blows up because it wasn't really sure what it was registering or subscribing to. So that's really kind of the idea behind ISO4. Now, ISO5, the connection management API, is really how do I send data from one point to another. So this is kind of like, I guess, your equivalent of IGMP in a, yeah, I guess IGMP in an MPEG over IP network with your joins and leaves of multicast streams. So typically for a receiver sending, or I guess receiving a multicast stream, you know, a typical MPEG over IP gigabit network, what it would do is actually join the stream that it wants and then leave the stream that it was receiving before. So in other words, you might actually have a burst of data on that particular network port or interface on the device where you would actually be technically receiving 2 streams at once. Okay, so that might be okay in a gigabit network with typical MPEG over IP bit rates. But when we're talking like gigs and gigs and gigs of information on 100 gig networks, that might completely kill a switch or a router, bring down a device. You know, we could easily oversubscribe any number of those ports by just not orchestrating that join and leave correctly. So we can't use IGMP technically with SMPTE 2110, or at least it's frowned upon, I guess. The proper way, or what I guess they're envisioning it to be like, is more of this control API of turning off a particular sender or making sure that you've left a particular stream as a receiver and then join it afterwards so that you're not oversubscribing. And then hopefully if everything's actually PTP synced, you know, that join and leave would happen instantaneously. As soon as your first stream has, you know, you've stopped receiving it, you would instantly start receiving packets for that next stream to give you a nice clean cut. You know, if you're doing like video editing or composing some kind of like a live event or something like that, you're not going to have a couple black frames or, you know, just null packets or something like that just sitting there waiting for a new stream. So that's what ISO 5 is all about. Now ISO 6 is the network control API, and this is really just configuring the devices, like the actual physical interfaces, like IP addresses of, you know, and subnets of the actual interfaces on products themselves, and then also just the routing, making sure that you're conserving bandwidth or not oversubscribing things. That's really what ISO 6 is aimed at doing. So, you know, with their powers combined, if you will, SMPTE 2110 networks would be, you know, much more smoothly orchestrated, and you're not stepping on anybody's toes in this way. Phew. Okay, taking a little bit of a break. Wanted to go through a couple questions from the audience. If you guys have some questions for me.
Yeah, we've got one here. Not sure if you can, yeah, does it support ITU-T G8275.2? Are you familiar with that one?
I think it's in relation to the PTP. Does the SMPTE PTP standard support this ITU standard, which is a precision time standard as far as I understand it?
Ooh, so that's an interesting question. I don't actually know the answer of it, but if, I mean, we can absolutely follow up after the call. I actually don't know. I know it really encompasses the IEEE 1588 standard, and then SMPTE 2059-1 and -2 were made based on that specifically for 2110 networks, which then you got to go back into then SMPTE 2110-10 and then actually look at how that applies to a 2110 network. So between those 3 standards, I am not familiar with the ITU standards. So I guess the answer is I'm not sure. But yeah, we can definitely take that one offline and go ask for sure and figure it out. Unless somebody's like got some crazy Google foo right now and maybe could figure it out.
We'll just, we'll keep moving.
Okay, cool.
Yeah. That's actually all we had for questions at this break, Aaron.
Okay, all right, cool. All right, so moving on to the next section, we've got adopting 2110. So just talking about some of the advantages and challenges of 2110 systems. I kind of hinted about the encapsulation technique before, and I did want to dive into that a little bit more here. And yeah, it's actually my next slide. So diving a little bit more into that topic with the independent packaging of videos and audios and things like that. Really what you're able to do is kind of construct a workflow that's extremely appropriate for the content that you're handling. It makes it way easier to you know, route between multiple components in a production environment. You know, when you have, say, like your video stream is going to go through switching, keying, graphics generation, you HDR mastering and color mastering and stuff like that. We're talking about pieces of equipment and functions that have to handle gigabits of data. Now, if you talk in terms of audio and metadata, why would you buy a piece of equipment that handles audio that needs to have gigabit worth of processing? That doesn't even make sense. We're going to be mixing audio, mastering audio. We're talking about megabits per second here. And then if you dive down into your metadata, you've got captions, the HDR metadata that comes from your HDR mastering, things like that. This is bits per second. This is the stuff that's added into your 2110-40 or generated by your 21-40 streams, and then go through an encode function and stuff like that. So this is the huge advantages of routing the individual flows through their appropriate functions and processes and stuff like that. You kind of break that apart, so you don't have an audio or a metadata generator that has to ingest, I don't know, 3 gigs, 12 gigs worth of information at a given time. So it's a huge plus in terms of just flexibility and things like that. And in addition to SMPTE 2110, there's actually, this is kind of funny, it's like an oxymoron a little bit, but 2110 actually has huge bandwidth savings compared to 2022-6. So before, when I talked about going from SDI to 2022-6, like literally taking your SDI streams, cutting them all up and dumping them into IP packets, that's the full SDI pipe literally being thrown onto an IP network. It's not efficient at all. And I actually think these percentages here on the very right-hand side of the screen give you a very good indication of the bandwidth savings that 2110 has over 2022-6. So we're talking anywhere from 16% to 40% efficiency gain in bandwidth. Just for handling video streams. And that's not even in addition to audio or the metadata streams, which obviously the benefits are a lot smaller, but bandwidth savings nonetheless. So it's pretty interesting stuff. And this is just for the uncompressed part of it. All right, talking about how 2110 kind of has its leg up in terms of our legacy. Maybe I shouldn't say legacy, maybe that's a bad word, but traditional broadcast SDI and coax infrastructure. Looking back at what happened with when we went from SD to HD, and we went from HD to 3G, and now we're going from 3G SDI to 4x 3G SDI, or even 12G SDI. I think there's like 48 SDI for 8K or something like that. Just crazy amounts of bandwidth and changes that you need to make to an SDI system when you upgrade to a new format. And what I mean by that is that if you want to do 4K and you had an HD SDI system, you have to completely pretty much tear out everything and rebuild your entire SDI infrastructure. Your cables aren't going to be able to carry the amount of bandwidth. Your SDI switchers aren't going to be able to handle that much bandwidth. It's essentially a ground up rebuild of your entire system. Now, one of the nice things about SMPTE 2110, it's IP based. It's routers, it's switches. Everything's going over fiber cables and things like that, and Ethernet. All of those things are rated for, particular data flows, and 100 gig switches are readily available and being deployed in many different types of applications. For a relatively, I shouldn't say inexpensive, but maybe affordable is the way to say it. No, that's a bad word too. It just makes sense for the amount of bandwidth that you're going to be moving around. It definitely starts to make sense dollar-wise to build a brand new, production system or a brand new content infrastructure around 2110 in, 25, 40, and 100 gig networks. Being able to move all of these streams kind of anywhere you want to in their own customized workflows and all that great stuff. So not only is it way more, I guess, easy to add bandwidth as it's needed, but also if anything comes along down the pipe, whether it's, is it high frame rate, is it HDR, is it 4K, 8K, millions of Ks, like who knows? You just really have to just tack on more bandwidth in order to handle the streams that that are needed for those particular types of streams. So, and obviously being IP based, it lends itself to server-based products virtualization, cloud type workflows and things like that, which I think we've all learned whether or not we wanted to learn or not in the last, year or so, given the current global situation. Obviously, doing virtualization and cloud-based workflows is huge in terms of flexibility, what you can do very quickly, what's quick to deploy, extremely flexible, all those kinds of things. Anyway, it just lends itself as a technology much more easily to that kind of stuff, just because it's IP based. Now, it's not all sunshine and unicorns when we're talking about SMPTE 2110. Obviously, there's going to be some bumps in the road. There's some difficulties with things. One of the things I highlighted a little bit in a previous slide was PTP synchronization over geodiverse networks. Local grandmaster clocks are an absolute necessary, with a particular, when you're talking about geodiverse locations, pretty much everybody has to have their own grandmaster clock, and then you have to sync those grandmaster clocks all together. So you have to have that kind of infrastructure, but then also maybe utilizing boundary clocks where the switches themselves act as a repeater, if you will, in order to kind of act as a kind of, what do I want to say? I guess a repeater was a pretty good description of it. But they kind of pretend they're a grandmaster clock and kind of handle all the device communication back and forth with those sync messages and delay requests that I was talking about before. The switch essentially handles all of that kind of communication between the end devices and the switch itself. And then the PTP clock just worries about being the grandmaster, clock, the extremely precise timing mechanism, and then everybody else does their best to be a boundary clock. Still, the best way to do it would be to have localized PTP grandmasters and then sync them all together, via GPS signal. Obviously, that would make sense. One of the other things we talked about already was the traffic shaping models. So your wide versus narrow versus near linear, all of those buffer models. Not every piece of equipment can talk with everyone else. Obviously, if you're a piece of equipment that can do that 720 packet buffering, you can talk with anyone. It doesn't matter if it's a narrow sender or a near linear sender or a wide sender. You've got the buffering mechanisms in order to communicate with everybody. Now, if you have a more hardware-based system, or you're much more worried about the time constraints and latency and things like that in your 2110 network, you might want to keep to those narrow and near linear buffer models, but that doesn't necessarily mean that every piece of equipment is going to play nice, especially as a receiver upstream. So it's just something that you kind of have to take into consideration when you're designing a 2110 network. Is everyone going to play nice, I guess, and speak the same language? A couple more points here. One of them is more not necessarily the technology itself, but more of a political, logistical, or maybe corporate culture even. But talking through NMOS control APIs, they are still maturing. They're still a work in progress. There's some more functions like more granular audio control and audio mixing APIs. Security is a huge concern. I think it's ISO 9. I probably should have wrote it on the slide, but ISO 9 and ISO 10, I believe, are specifically around the security of the actual API itself. Right now, there really isn't anything, so anybody could technically intercept your control API and wreak absolute havoc on your 2110 system. Now, obviously, that's a doom and gloom description of the problem. But it's definitely a huge concern. In modern IT based systems, network security is huge and very very hot topic, very high priority. So the NMOS control stuff needs that stuff in order, I think, for people to feel secure, like they've got stuff locked down. One of the other things is there's a lot of proprietary solutions out there. There was quite many early adopters of 2110 in terms of just transport. So in other words, just getting video into 2110, dumping it onto a high bitrate IP network, and just kind of doing the early adopter thing. But along with those early adopters came some proprietary control mechanisms that not necessarily everybody can interface with or are allowed to interface with. So there's some interesting, I guess, situations that you know, people with systems that have these proprietary solutions can get into when, you know, maybe one piece of equipment just simply can't communicate with another piece, which in terms of, you know, like I was talking about with all the NMOS control APIs, the idea is everybody plays nice and speaks the same language when orchestrating a 2110 system. And if that doesn't happen, it can get kind of ugly pretty quickly. I did want to call out SDP and SDP over SAP. So SDP is essentially a file that's generated. It actually just mimics what NMOS ISO 4 is doing right now. So it's that registration and discovery and telling people, hey, I am sending these streams on these IPs. This is what those streams are made up of, whether it's video, audio, or metadata or something like that. The SDP file is literally that. It's like an exported file that gives kind of a table of contents of what a particular transmitter is sending. You would then import that SDP file into a receiver, and then the receiver kind of automatically just knows, oh, hey, I will subscribe to this stream and this stream and this stream, and I know exactly what's in them. It's that table of contents that I was talking about, but in a very kind of archaic way of like, you know, exporting a file from a piece of equipment and then importing it into another. Like, okay, that's like, let's adopt like a really cool new technology like 2110 and then use file stuff for like subscribing to streams. The next iteration of that was SDP over SAP, was essentially doing a multicast of the SDP information across SAP, which is just it's a kind of a multicast announcement protocol is really what it is. And it just announced all of the SDP information on the network. And then you would subscribe to that multicast and it would essentially build kind of a table of contents for you as a receiver. And then you would subscribe to it. That's essentially what ISO 4 from NMOS is in a much more elegant way. But anyway, it was a early, but let's just say ineffective solution. So some of that stuff's out there. So the next big thing is really it's 2110 is an IT heavy system and really can be difficult for some people and some organizations to manage or be able to plan. Brad Gilmer actually had a really, really good discussion at VidTrans this year in California. That was back in February. He did a presentation on IT thinking in professional media. And it called out, I mean, it actually pretty rawly called out, you know, just the industry in general and how, you know, sometimes we're IP centric, other times we're like so stuck in our ways that maybe we're not able to adopt technologies like this quick enough. But he made a lot of good points about you really have to be an IT centric organization in order to drive, maintain, deploy a 2110 system, just because, you know, like the slide says, it's an MPEG over IP network times 100. Like, you're just crazy amounts of bandwidth. You've got APIs that are controlling absolutely everything. And then also software defined networks to be considered as well. So it's just a lot of, you know, IT type stuff you have to learn. So talking about what's up and coming, wanted to talk about light compression in 2110. So we've been talking about uncompressed like crazy. But one of the big things that's coming along is ST2110-2022, which is a constant bitrate compressed video standard. So this is for light compression over 2110, extremely low latency. And the technology that's kind of taken the lead in that conversation is JPEG XS. At least in my eyes, it's been JPEG XS. We're talking about near lossless or visually lossless compression with less than a millisecond of latency. You can get 4K streams down to HD bandwidth, which is incredible savings when you're talking about doing uncompressed stuff. And if you can take the hit in latency, a combination of these two technologies, in addition to the flexibility of a 2110 system with independent flows and things like that, is not only a huge bandwidth saver, but, well, I guess that's it. It's a huge bandwidth saver and maybe a money saver, I guess, in that case, and not having to maybe not lease as much bandwidth or what have you. And then, of course, NMOS. It's still a work in progress. Oh, yeah, here's the thing where I actually talk about ISO 9 and ISO 10. So talking about the system APIs, but also securing the communications in the API so that everybody has the warm fuzzies that their orchestration network is definitely secure and can't be hacked or messed with or anything like that. Whew, okay, that was a lot. I'm sure we have some questions. Do we even have time for questions? Maybe we should leave those for the very end, and I can talk about some 2110 products for Sencore. In fact, maybe I'll just do that, just so that everybody understands kind of what Sencore has been doing lately, the products that are kind of highlighted with 2110 systems, so that you guys have an idea of what solutions we can provide. And of course, if you have questions or want a deeper dive into any of these products, please let us know. And obviously, we'll be doing some YouTube streams and stuff like that to kind of highlight these products individually as well. So be on the lookout for those. But I'll go ahead and dive into these right now, and then we'll do kind of a final Q&A for everyone at the end. We'll catch all the questions. All right, so got quite a few products to talk about here. So first off, I did want to talk about the VB440. This is our SMPTE 2110 analyzer. This has been a huge splash in the market. Awesome feature set. I think it's, I mean, this might be a biased opinion, but I think there's a lot of people actually on the call that might agree with me. But that is leaps and bounds better than I think the competition, and the feature set is awesome, and it has really kind of helped us drive our 2110 implementations with the rest of our products. Then of course, you know, I work for Sencore, so I got to talk about our receiver decoder platforms. Talk about the MRD 7000 and AG 6000, got some 2110 outputs there. Also our DMG 4000, our media gateway platform, and then our SDI 2X, which is our SDI to 2110 converter. So kind of a simple throwdown type deal. But going into the VB440 a little bit deeper, this is our analytic platform that's able to subscribe to 80 gigs simultaneously of 2110 streams. So we're talking about video, audio, metadata, grouping those streams into you know, relevant groups of channels, and analyzing them all together, and looking inter-arrival times, and you know, waveform analysis, color space analysis with a diamond view, like all kinds of things that you would expect you know, in a waveform analyzer, but then also combining that with you know, what we've had in our Video Bridge product line, like looking at the IP analytics, the jitter, the packet loss, stream timing, everything brought together in this kind of all-in-one platform for 2110 analytics. And we've got support for other formats like 2022-6, and also looking at hitless switching, so SMPTE 2022-7. All of those kinds of things. So some of the new things that we introduced in 2020 was SCT 104 and ST 352 analysis and logging. We upped the bitrate from 40 gig to 80 gigs. Kind of highlighted the diamond view a little bit, but that's the color space analytics. So actually looking at your BT 709 and BT 2020 color spaces in a nice diamond view. And then also support for NMOS, ISO 4, 05, and 07 as well. And one of the huge things that has been a huge up, I guess, against the competition is that this platform can actually be simultaneously accessed by 8 separate users via a web interface. So this isn't like a little screen that you sit in front of. You can actually access from your, whether it's your computer, your laptop, you know, even your iPad or something like that. You can log into the interface and look at every single stream this thing has been subscribed to, look at live video thumbnails, all of the IP metrics, everything, and you can have 8 people log into it at once and have full access to all of the information that it is providing. So awesome engineering tool, awesome operations tool, whether it's a, you know, live production type system or a lab system, and you're just getting started. I think this is like an absolute must-have tool if you're getting started. Otherwise, you're just kind of shooting in the dark, to be honest. It's super high bitrate stuff, and so you need something. You need a platform that can accurately tell you what's going on in your network. All right, moving on to the MRD 7000. So this is Sencore's newest software-based decoder platform. Lots of new features introduced in the last, I would say 4 to 5 months, but really what this product is it's a multi-channel, multi-codec decoder with really options for just about any input and any output you can think of. So we can decode HEVC, H.264, MPEG-2, all the way up to 160 megabits per second. So we're talking UHD, 60 frames per second with HDR, wide color gamut, 422 10-bit. You name it, throw any kind of compressed video at it, and we can decode it. What's nice about this is specifically around the 2110 conversation is we can actually do a compressed video decode, say from satellite or a Zixi or SRT or RIST or MPEG over IP stream, or even a file-based input, do the decode and then output 2110 instead of SDI. What's really important here is, especially from the file-based input, you can actually take all of the content that you've had for years, you know, for recorded live content or streams that you've been using for testing or something like that, load that up on the MReady 7000, click play, and it will decode those compressed streams and kind of fuel a 2110 network that way. So it's really good for lab environments and stress testing, 2110 networks and things like that. So extremely flexible platform in addition to the contribution and distribution decode capabilities. So awesome new platform. Then I also wanted to highlight the AG6000. So this is our ASIC-based decoders. I think everybody's pretty familiar with our Atlas Gear line of decoders, but this is a new introduction that we can decode HEVC, H.264, and MPEG-2 streams and actually output SMPTE 2110 natively on an ASIC-based decoder. And so really what this gets us is a very cost-effective, very low cost per channel decode of 10 channels in 2RU with 2110 output. Which is extremely competitive against pretty much everybody that's out there. So if you need to do a lot of, you know, whether it's satellite or MPEG over IP, decode and fuel a 2110 system, whether it's for re-encode, for monitoring, for production, what have you, this is a very dense, low cost per channel platform for fueling a 2110 network. We got our big dog DMG 4000 media gateway platform. So this is a hardware-based platform that is essentially well, I mean, it is a media gateway platform. Anything from transcoding, decoding, encoding, even if it's light compression stuff. So we're talking about HEVC, H.264, TICO, JPEG 2000, 2110 streams. It's really ingest and output literally anything. Up to 2,500 streams with 10 gigabit connectivity. This can be your kind of, what do you want to say, video firewall, video router almost, whether it's compressed or uncompressed. We've got inputs, outputs, and all the functionality to support, you know, encoding, the decoding, the turnaround, multiplexing, all kinds of crazy stuff. So yeah, very, very powerful, very, very powerful platform. Then last but not least is our SDI2X. This is our SDI to 2110 gateway platform. So this is specifically for SDI to 2110 turnaround. And I don't mean just SDI to 2110. We can go to 2110 to SDI as well. But really this product's focused at, you know, kind of bridging the gap between those uncompressed IP networks with 2110, 2022-6, and then turning them back around to SDI and HDMI. You know, there's a lot of systems out there that, you know, either don't need to be rebuilt, but also need to be able to accept 2110 system or signals, and vice versa. Maybe you have some legacy SDI infrastructure that you need to get, you know, into a 2110 network that's been newly built. This is the perfect platform for that. We have a throwdown box that's able to do 1 to 4 channels of 2110 to SDI turnaround, as well as an open gear card that is able to do 40 turnarounds in 2RU chassis. So extremely dense. Very cost competitive against the other vendors out there that are doing similar stuff with the turnaround products, but yeah, good product. All right, so I have talked for what feels like forever. I do want to open it up for the final Q&A session. You know, thanks everybody that's attended. It's good to see these this amount of people interested in what we've got to say about 2110. But yeah, I'll open up the floor for questions.
All right, Aaron, we got quite a few here, so let's just try to pick off as many as we can. Try not to keep everyone too long here, but the first question is, how are ad markers and closed captions handled, as well as does 2110 support HDCP?
Well, so the ad markers, which I'm assuming is probably talking about SCT 104 and closed captions, so that actually all rides along just fine in the SMPTE 2110-40. So that's our metadata standard. And I'll actually just quickly go way back here. This guy here. So really anything that exists from ad markers like the 104 messages and closed captions and stuff like that perfectly fits into this standard. We can essentially translate it into an IP packet using the DID and SDID that really exists in SDI and dump it right into a 2110-40. So you really don't need to do anything differently here. Obviously the 2110, transport mechanism is way different, but in terms of what you need to do in terms of formulating the data, how you use those add markers and things like that will be the exact same thing in 2110 as it was in SDI or even compressed. So yeah. What was the other one? HDCP?
Yes.
Yes.
So that's an interesting question. Talking about HDCP, which is HDMI, and then whether or not that's in 2110. Oh, okay, I kind of see where you're going with
copy
that.
protection.
Yeah, copy protection in uncompressed land. I don't think it supports HDCP specifically. Wow. Yeah, that's a really good question. I don't know. I don't think there's any kind of security mechanisms for, what do I want to say? Yeah, copy protecting your 2110 streams. I don't
Aaron,
think,
wouldn't that be up to whatever device is supporting the HDMI ingest and not necessarily the 2110 protocol?
yeah, actually, I think that's a very good way of describing that. Yep, probably.
Yep.
All right, couple more questions here. Do all switches and routers need to understand PTP messages? Can we use a network device without PTP support and only transmitter and receiver synchronize?
Yeah, so that's actually a really good question. Really what that comes down to, you don't necessarily have to have a router or a switch that understands PTP, and I've actually played with this quite a bit. We have some Mellanox and Cisco 25 and 40 gig switches here at Sencore. You can make them do their normal switching and routing, I guess what they would normally do, without having PTP enabled. And everything works just fine. The thing is, you got to be really careful about how many actual devices you have on a network, because what it comes down to is if your PTP clock, your grandmaster device, can handle the communication, so that back and forth sync messages and delay requests and stuff like that that happens between the grandmaster clock itself and all the devices on the network. Depending on what clock you have, maybe they can only handle 50 devices or 200 devices or 1,000 devices or something like that. It scales quite a bit differently. Now, if it can't, that's when your router or switch needs to be able to understand PTP and become that boundary clock or that PTP repeater. So instead of having the actual PTP grandmaster clock itself doing all that communication between all the devices, the switch kind of takes that on as a buffer and says, all right, I'll handle all the communication. I'll sync all you guys up, and then hand off just pertinent information to the PTP grandmaster. So that's more of a, how many devices can your PTP clock handle? And if you have too many devices, then yes, your switch and stuff like that needs to handle that stuff. Otherwise, like in a lab environment with, I don't know, maybe 20, 30 devices or something like that. Even in our labs, we haven't had any problems just putting the grandmaster on it, making sure that multicast is being routed correctly, and it's off and running, so it shouldn't be a problem.
All right, and another one here. What is the technical reason why IGMP is frowned upon in the standard?
It's just frowned upon because with IGMP, like I talked a little bit about, was with IGMP, you're doing an IGMP join and then you do an IGMP leave in that order. So in other words, if you're already receiving a 2110 stream at 8 gigs a second or something crazy, and then you want to join a different stream, you're going to do a join first, which means you went from like 8 gig to 16 gig potentially. These are bad numbers, but whatever, you get my point. Now you've essentially overdriven not only the interface but also the switch interface in that join leave, that IGMP join leave, where NMOS and any of the control APIs make it so that you're not joining and then leaving. What essentially happens is the first signal is turned off, and then the second signal that you're going to be joining follows, essentially directly after. So that way it's a hitless switch between two different signals. So it's just a different way of controlling the join leave piece of it, where IGMP is, like I said, perfect for an MPEG over IP network, gigabit network or something like that with compressed streams. When we're talking about doing 2110 streams, it's bandwidth sensitive. I think that's probably the best way to say it.
All right, Aaron, here's one more question. Do you foresee the availability of a hybrid SDI 2110 router?
Yeah, I actually kind of think some of that exists. I know there's some SFPs and stuff like that that do essentially like a 2110 SDI turnaround. Yeah, I think that stuff kind of exists already, actually.
Okay, here's one. Where does HDR metadata live within 2110? Is it in the ANC flow?
Yes.
Also, will the SDP reflect this HDR info?
Yep. Yeah. I mean, the answer is just yes. So actually, the slide that I have up right now, HDR10 and HLG, and I think any of the, like the HDR pluses and things like that will ride along in VANC anyway. Well, I mean, I'm trying to think of what standards they are. SMPTE 2096 and 2108 both carry data for wide color gamut and HDR to signal those kinds of things. So those would go right along in 2110-40. And then speaking towards the SDP stuff, so that would be either SDP or NMOS ISO 4. There is actually a very detailed list of what kind of, let's see, color telemetry, whatever HDR format and stuff like that, that's actually described in the video metadata, if you will, in the SDP and NMOS ISO 4. It calls that out very, very specifically. Is this stream HDR? Is it 1080p 60? Is it 422 10-bit? Is it all of those things? And that HDR and wide color gamut signaling is definitely a part of that.
All right, thanks, Aaron. I think in the interest of time here, we still have some more questions, but I think we should go ahead and wrap it up. We can get some of these other answers out after the call and answer those one-on-one.
Yep. All right, cool. All right, everybody. I think that that wraps it up. Thank you so much for attending. I thought that's went very well. I hope everybody learned something, had some good takeaways. Feel free to reach out to any of us, whether it's me, Jason, or Seth. Our contact information is in the slide. We will be making this presentation available after the fact as a recording. One of our marketing people, Chelsea, will actually be sending an email to every single attendee here and even the people that missed it to be able to watch offline and take notes and look for errors in my presentation and things like that. So yeah, be looking for that, and also be looking for any of our announcements for future webinars and YouTube content as we try to feed as much information as you guys to you guys as we can with you know, without NEB being there. And I think these are important. So thanks a lot for attending. Appreciate it. Have a good day.